so I'm actually going to write down two integrals. The first one is the integral of x squared times e to the x dx versus the integral of x times e to the x squared dx. Very similar looking integrals, very different techniques for analyzing these two integrals. The one on the right, when I see this one thing that I notice is that the power on the e is an x squared. And whenever I have fancy stuff up in the power, I want to think of that as an inside function. And so when I look at that, I think, oh, what's the derivative of x squared? It's 2x. And I see an x out here. So this example right here, where the power is fancy and its derivative is showing up somewhere else in the problem, this is a good candidate for a u sub, where u is equal to the exponent, the x squared. So that one I'm going to leave for you to test on your own, but that one is more of a u substitution. Now, the other example, the integral of x squared times e to the x, now the power on my exponent is just a plain x. So that is not a good choice for a u substitution. And if I choose e to the x as my u, the derivative is not going to help me cancel stuff. And if I choose x squared, I still can't get rid of the e to the x. So this guy right here, x squared e to the x, is not a good candidate for a u sub. A better choice here, when you have two things that are multiplied together and a u sub doesn't work, is integration by parts. So the integral of u dv is equal to uv minus the integral of v du. Okay, so up here, this other one I'm going to box off and leave that for you to do on your own. And now let's look at integration by parts. Okay, so I write down my acronym, LEAT. And I notice that exponential function is at the very end, so I'm very likely not going to choose u to be equal to e to the x. Starting on the left, no logs, no inverse trig, but I do see an algebra. And so my algebra is the x squared. And so I've got u and v and du and dv. My choice for u will be the algebra, which is the x squared. And everything else, the e to the x and the dx, is my dv. All right, so I'm going to need the rest of this table as well. So the derivative of u is du, and our derivative of x squared is 2x dx. So I've moved that dx over in my head. And going from dv back up to v, I need to take an antiderivative. Antiderivative of e to the x is e to the x. That one's easy. Sadly, if this had been e to the 3x or e to the 5x, we would have had to do a u substitution to get back the antiderivative. Okay, questions or comments so far on the information we have? All right, so now we're going to look at uv minus the integral of v du. Okay, so we have the integral of x squared e to the x dx is equal to u, x squared, times v, which is e to the x, minus the integral of v, e to the x, times du, which is times 2x dx. All right, so as I mentioned before, here's an integral that we will want to simplify before we analyze it too much. So we've got x squared e to the x minus, here I can pull that 2 out. And we have the integral of x times e to the x dx. Okay, so I take a breath and I look at this and I say, all right, the x squared e to the x at the beginning is done. I don't have to worry about that anymore. This integral, however, is still two terms that are multiplied together. U substitution is not going to work. I don't see any U sub that I could do. I, at this point, want to ask myself, am I better off than when I started? And when I started, I had an x squared times e to the x. And now I have one less x in here. So I am better off than when I started. However, I'm not done. In this example, I'm going to have to use integration by parts again on this integral. All right, so integration by parts again. And so now, again, I'm going to build my table. U and V and du and dv. I look at my acronym and I choose the algebra, so u is equal to x and dv is equal to e to the x dx. My derivative of x is 1, dx tacked on the end. Antiderivative of e to the x is e to the x. Okay. Questions so far? Okay, so we can copy down with quotations x squared e to the x minus 2, and I'm going to have to put brackets in here. Okay, my antiderivative will be uv minus the integral of v du, so uv, we've got x times e to the x, minus the integral of v, e to the x, times du, which is just dx. And I look at this again and I say, okay, do I need to do any simplifying with the integral? No, there's nothing to simplify. Am I in a better place than I was before? The answer is yes. I've totally gotten rid of all those x's in there, and I know what the antiderivative of e to the x is. So this one, we know, and we can finish out the problem, x squared e to the x minus 2 times x e to the x minus e to the x. And since we're now done, we can tack on our plus c. So this is our final answer, which you can certainly distribute that to and combine like terms if there are any. All right. So the moral of this story is that using integration by parts is not necessarily a once and done deal. If I had given you one that was the integral of x to the 10th times e to the x dx, you'd have to do this 10 times over. Each time you'd knock that x down by 1. Okay. So integration by parts. Any questions about that? Yes?
When you integrate by parts, then basically the second time we did it, we just moved the doing the antiderivative to the inside. So by integrating by parts, you're basically getting rid of
one of the x's.
Yes.
Yes, that's in this style of problem where you have x raised to a power times e to the x, that's exactly what you're doing. Okay, other questions? All right, so let me tell you about some practice problems that I'd like you to look at.